clock signal. I built a 4-bit ring counter, which verifies that the whole system works. And so I will be going over my process on that. So starting with the system controller, I'll open this up. This was basically the core of the design. Instantiates the ClockWiz 0 IP, which I configured to take 125 millihertz input clock and generates two outputs, the 125 millihertz clock and a 100 millihertz clock at a 10% duty cycle. So the file contains critical reset logic. It takes the reset in from the board and holds the system reset out high until after the clock wizard's lock signal is asserted, plus an additional 32 cycles. And this ensures that the whole system is stable before it starts. The next part is the shift left ring counter. This was a simple 4-bit counter which performs a left shift every clock edge. It's designed with a synchronous resets that initializes at 0, 0, 0, 0, 0, 1. So 3 zeros and then a 1. And an enable port, so it only counts when the enable is at a high. And then lastly, there is the top. This is the structural code. The prior two codes were behavioral. So this one is instantiates the system controller. It takes the two clock outputs, clock out 1 and clock out 2, and wires them into the buffg mux primitive. So this is our clock multiplexer and is controlled by the clock mux input, and the output of the mux then goes into buff GCE, and this is a gated clock buffer controlled by the clock gate input. So the top module outputs the final clock out and reset out to be used by our counter in the test bench. And the test bench we have here. Just an overview of that. I will run the simulation. Just to confirm that everything's working, I decided to run the simulation in real time. So far, no errors, which is good. And yeah, this is our simulation results. I will expand out, zoom fit it, and as you can see, everything worked at plan. So just kind of an analysis of this waveform here. We have a couple parts. First, we have the reset sequence. So at the start, the S locked is low, our system reset out correctly stays high. S locked goes high at around roughly around 404 nanoseconds. You can see it here, it's a little bit off. And then the reset out correctly goes low at 32 cycles later at 660 nanoseconds. And at that exact moment, the S counter is reset at 0001. So test 1 and 2, that's the clock mux right after the reset, TB enable, and the TB clock gate are high. And with TB clock mux at 0, the 125 millihertz clock is selected, and the counter cycles. So we have it's 1, 2, 1, 2, 4, and 8. And then for test 2, we have TB clock mux set to 1. And if you can see here at the S clock out, the pulses get wider as it switches to the 120 millihertz clock. And that counter just continues to count, but slower. And this pretty much shows that the mux is in fact working. Test 3, it's at 716 nanoseconds. We're testing the clock gate by the TB clock gate at 0. The S clock out signal stops immediately, as you can see, and then the S counter freezes its value at 4. And that's where you get this 4 over here coming from. And that confirms that the buff GCE is in fact working. And then the last two tests are the counter enable. We set the TB clock gate back to 1, resume the clock, but we set the TB enable to 0. And the S clock out resumes, but the counter correctly stays frozen at 0 here. And then test 5, it's setting the TB enable at 1. Counter immediately resumes counting again where it left off, and then advancing from 4 to 8. So that's why we have 8 here for the S counter. And then just kind of confirming with the TCL module, we do have it here, all tests passed. So the simulation confirms all components, the clock wizard, the reset logic, buff Gmax, buff GCE, and the counter are all working correctly. Thus, we got a successful experiment. And that concludes this video. Thanks for watching.